Okay, welcome everyone. I will give everyone a couple more minutes to join us. At 10, we'll start with the introduction, and we'll give each of our presenters about 45 minutes more, give or take, for their part of the presentation, and we'll leave some time Q&A.
I think Dr. Elahinia is free. Is it only for me or also for you?
No, same here.
Same here.
Okay, same here.
Oh.
Okay. Dr. Elahinia, can you hear us?
I hear you guys. I'm not sure.
Okay, for a few seconds we couldn't hear you.
Okay, so is it okay now?
Yeah.
All right. Okay. Good morning, good afternoon, good evening, everyone. I know we have participants at least from 3 different continents, if not more. I am honored to be moderating this session of AM Smart. This is an idea that was developed and executed by Professor Mehpuya, who we have also here present on the webinar. He's a professor at the University of Twente in the Netherlands. And today's session is dedicated to additive manufacturing of shape memory alloys. We have 2 esteemed speakers, Dr. Benafan from NASA Glenn and Dr. Qattawi from University of Toledo. I don't want to take more of your time other than inviting you to connect with AM Smart, follow on LinkedIn and other social media, register to receive the newsletters. The intention for the organizers is to continue this with a frequency about an event for every 2 months. So that's a great opportunity for the global community to come together and learn from each other and further build the community. So without further delay, we haven't decided on who goes first. So I leave it up to you. If Allah, you're ready, you can go ahead and with your presentation.
Oh, okay, thank you. I don't have a preference to, I mean, if Dr. Benafan wants to go, that's fine.
It's fine with me as well. Othmane, do you have a preference?
No, no preference. It's okay.
Okay, then Allah, you can go first.
Okay.
And for the audience, if you have questions, please feel free to type them in the chat as the speaker.
Okay. Do you see the full screen?
Yes.
Okay.
Yes, we do.
Okay, good morning or good afternoon or good evening for everyone attending today. Thank you for making the time. So today I'm gonna give you a brief summary about the recent additive manufacturing project we have been exploring for an iron shape memory alloy in my lab. So I work as an assistant professor at University of Toledo. My lab is focused on integrating design and manufacturing aspect. And this project had been the focus for the past 12 months with various funding from National Science Foundation and Toyota Research Institute. So as an overview of the shape memory alloys, most of us aware of the nickel titanium based alloys that has been extensively explored because of their relative great properties, corrosion resistance, and good strain recovery that can be achieved by nickel titanium. However, there are also different groups that we can focus on for shape memory alloy that's based on iron shape and then copper-based alloys. So relatively most of the shape memory alloys systems behave with a certain procedure or certain phenomena that's similar to regardless of the composition of the alloy system. So we either have shape memory effect or super elasticity effect, where the material basically responds to a stimuli and then return to its original shape or original geometry because of differences in the microstructure. So in other words, the material remembers its previous set or previous pattern or previous structure on the microstructure level, and then goes back to that after a stimuli. Now, there are various applications where we can focus on shape memory alloys, especially for metals that has high strength, high elevated temperature applications. And one exploration of the iron shape memory or different alloy system other than nickel titanium comes in as of interest because of new manufacturing processes that enable us to get more insight of how to design this material or control it. So the particular interest in our research is iron, manganese, aluminum, nickel alloy within the iron shape memory systems. So historically, using traditional manufacturing processes, the iron shape memory has a good strain recovery. It has a varying strain recovery percentage that can be up to 13.5%. And then we have lower cost and good workability because of the presence of iron in the alloy system. And then with all the research that has been done in a traditional manufacturing of this alloy, we also know that it showed more ductility and small temperature dependency of the critical stress. So technically, if you can see the figure on the right, mostly the nickel titanium will reduce its efficiency in performance as we increase the temperature. And this is not the case, has been proven for the iron shape memory alloy. So there is a potential if we can understand how to manufacture this alloy system carefully and understand the correlation between process parameters and then the microstructure, there is a window where we can leverage this phenomena in the alloy system. Another studies also has been done on particularly this iron manganese nickel aluminum alloy system is for high temperatures or applications where there's a high variation of temperatures, for example, like aerospace or space exploration. And you can see there is a window where this alloy system potentially can behave or perform with a transformation temperature strain that's actually very good and desirable. So certainly there is a window and a potential for exploring these systems of alloys. Now, one question can be paused is if we are already establishing a process through nickel titanium, through casting and induction vacuum melting, why we just don't explore the same processes and continue with the iron shape memory alloy and explore its potential. And what we know also from this characteristics of the alloy system is that it's very susceptible to changes in the processing parameters, even in the traditional one or in potentially in the additive manufacturing one. So what we can understand is that the cooling rate, for example, the thermal temperature and thermal changes across the process when we manufacture this part can change the grain structure. And this significantly can also affect the performance and the super elasticity that we can get from this alloy system. So potentially, what we're saying is that this alloy system has a potential. It can show better strain recovery and less dependency on the critical stress on temperature. And if we understand the process parameters carefully, then we can design this alloy system and structure in order to get the needed properties. And this way of thinking is not new to additive manufacturing field, right? So the additive manufacturing has started with understanding how to manufacture a part, what will be the material properties, correlation between the structure, the material, and then eventually the component. And then we are in a phase now that we mastered the initial processing parameters, and now we want to do functionally graded materials. This can be with the different metals or different alloying systems, or even within the structure itself. So if we can localize the mechanical properties via microstructure properties in any alloy system per the need of where this material will function, then we can technically control the whole design of the material from the microstructure and up to the component. So this idea is not new to additive manufacturing, but it gets its critical importance when we talk about shape memory alloys and structures that actually needs to change and fold or unfold or behave in a certain way in the service conditions. And that will give us a fourth dimension, technically, that we can apply to in addition to the third dimension, which is a structure, in order to design the full component from the micro scale up to the component scale. So you can see, for example, here that if we changed the the processing parameters on a laser powder bed fusion machine, that will yield totally different microstructure within the same composition of the powder, same composition of the component, everything the same. The only changes is only the processing parameter. So basically how much energy we're pulsing on the powder in order to melt it and create the part. So eventually we will have a different mechanical properties if we control this process parameters. So our analysis started with a customized powder. So if you are in the additive manufacturing world, you know that powder is the most critical component of getting into additive manufacturing. Other than the well-known alloying systems, there's not much production for a customized powder. And it's also a process by itself to how to control the powder, the shape of the powder particles, the composition, and etc. So the first step was to customize this powder and have a collaborator who can actually produce this powder with the required composition and a variation of the composition too. And I want to add, like, this composition that we used is not something we just came up with. It's historically and scientifically proven to have shape memory effect or super elasticity based on the traditional manufacturing processes. So we started with what we know in this alloying system that proven to have shape that have to have shape memory effect. So we started with a laser powder bed fusion machine with a heated plate, as you can see, that is not heated. So another technique that we introduced in the IDM lab is that usually we lay the powder and then we have a laser that goes scan into lines or whatever the pattern is, and then create the final component we need. Because of the differences in the thermal energy that's dispersed across the part, we have a huge residual stresses across the component and the material because the plate is actually cold, and then the powder is the material that's getting all the heat from the laser. And once the laser passes, then there's a significant thermal reduction or thermal energy loss from the powder or the component to the plate. And that's like all this dynamics of the thermal energy is actually making all different problems in the production. So what we introduced is that in-situ heating. So during the whole heat, we have a heat-assisted process. So the building plate will stay up to 500 or 600 C while we're printing, and that's what reduce the residual stresses, reduce the thermal inconsistency across the building plate, and significantly improve the quality of the parts that we actually producing. And in some research, other than the iron shape memory alloy for like super alloys like nickel, this has proven to even heat treat the part or the material while we are printing. So we actually reducing the number of steps we have to do in order to produce the part. And all of these conclusions came through in situ thermal monitoring of the production. of the metal. So you can see on the left, we started with basically a very wide window for where we are, because we need to optimize these process parameters until we reached a point with thermal monitoring and understanding of the defects that each window yields, until we reached a viable possible material that we can actually test with acceptable porosity and an acceptable density that we need. The other thing also is for thermal history effect is with all this collective data that we have on the machine, or generally in laser powder bed fusion, scientists are trying to understand two things. The first one is if we can predict what will be the defects in any material while we are printing, so the machine can stop, correct its path based on the images it's actually collecting, and then improving the quality of the material we produce. And then the second aspect is to understand if we are able to predict the mechanical properties out of the thermal imaging. So if we collect certain amount of gigabits from the machine while we're printing, and then we already know the mechanical properties of the tested coupons, then can we correlate that? In other words, we also control the thermal properties by controlling the quality, and then by understanding the prediction of the mechanical properties that we're going to produce. So eventually there's no need for testing with machine learning if we can. So the collective of this data will be correlated to the mechanical properties we get, and then eventually the shape memory properties in the material. And to give you an insight of how this looks like, so we collected many images through the print. So like each sample can have millions of images across the whole print, because we take like one image every 30 seconds, or if I'm correct, 20 seconds. And then this all layers needs to be on top of each other to get the whole part. But to give you a glimpse of what this data looks like, so if you looked at the thermal effect for cooling rate, you can see for each of these samples, they have a different laser power and different laser speeds within the same alloying system, the iron shape memory, but we results in a different cooling rate. So in other words, the material, because of the thermal energy that we disperse, can have a different time to cool or goes to the temperature of the building plate. And this, like over aggregation of time and over aggregated layers, this makes a huge difference at the end, because eventually we can spot where the thermal cooling rate was irregular. And that will give us exactly where the defect happened, in which layer, in what time, in what place in the sample. Eventually, after aggregating all this data, we reached an understanding of the laser powder bed fusion for iron shape memory alloy. And you can see the differences in the quality of the print, like the consistency, the shiny surfaces that you can get. All that is an indication of good print. Of course, it doesn't conclude how much porosity you have or micro defects in the samples, but yet it's a starting point for any additive manufacturing exploration of materials. We also looked at understanding the microstructure in terms of defects. And then you can see here the extremes of the two windows. So if we have low energy density, you can see a lot of defects that are happening on the microstructure. So we have irregular voids, we have cracks, we have small pores, like particles of uncentered powder, that the dynamics of the melting pool affect the quality of the sintering. And then on the other hand, on the high energy density, where we have high laser speed and high laser power, we can also see some certain defects. And if you are in the additive manufacturing world, you'll understand that actually, though additive manufacturing is a very viable process to produce materials, we are limited in the window where we can get a viable, good mechanical properties of any material. So even in the high energy density that's processing very fast to increase the production rate, we still see a lot of defects. And this was one of the optimization where we need to be in a good window for the iron shape memory alloy, and at the same time reduce these defects on the micro scale. So in this recipe that we're producing, we also looked at the scanning track morphology. And then the scanning track morphology is looking at how the scanning procedure basically mend and fuse the powder together. And then you can see with the different scanning strategies and different scanning speeds in powder, you can see there are also some defects, discontinuities that can be produced. And then with all this information that we get from iron shape memory alloy, it may be correct for this certain alloy system or its variation. However, in laser powder bed fusion, we cannot predict that for all alloying systems, and that's why it needs to be done every time we're exploring a new composition of a powder. So for example, aluminum alloys is known to do certain behaviors within the laser powder bed fusion, and so does the iron shape memory alloy. So every powder composition has its own unique behavior and reaction to the processing parameters. The next step in the analysis was, okay, we produced a good part. It's shiny surfaces. The surface roughness is acceptable. Hardness is acceptable. Density is acceptable. Now it's the time to look at the mechanical properties of those components. And then the initial study is that we actually achieved good values for the strain recovery within this alloying system. Now, when we talk about good recovery, that's not the optimized one. Hopefully, when we reach the point where we understand completely the effective processing parameters, and we spotted this small, tiny window where we have no problems, we have no defects, we have good track morphology, good microstructure, etc., then this is the area we need to optimize. But initially, the alloy system showed promising strain recovery around 50% between loading and unloading. And then as a regular alloying system that will have high loading, we looked at the modulus of elasticity. And then in this technique also, we applied a manufacturing technique called remelting. And remelting is basically the same as processing the material, but instead of the laser passing one time, we tried to do it a second time. The remelting not necessarily will have the same energy and laser power, speed, and power, same to the initial scan, but it serves two purposes. The first one is reducing any microstructure defects that actually happened and the laser at the first time couldn't get and center the powder. And then the second objective is to somehow treat this material with the laser in order to basically get the bulk material that we need. And this technique, it reduces the speed of the production, but it still improved the modulus of elasticity for this specific alloy system. Now, one problem we found in this alloy system is the unpredictable brittleness of the material. So you can see, for example, in certain laser powers, you can achieve with the as-built. So basically one laser pass manufacturing the material will achieve low elasticity and this basically high hardness, and the material is brittle, so we cannot even get it out of the building plate in one piece. But with remelting for each layer, that can be improved, and we saw a significant improvement in the modulus of elasticity and technically the hardness, reducing the brittleness of the material. We also looked at nano indentation specification. So basically, we looked at the microstructure on the nanoscale in terms of plasticity. And plasticity index is a correlation between the hardness and the modulus of elasticity of the material. So it measures the ability of material to resist this indentation and gives you more in-depth characteristics on the microstructure. Because of inconsistency and the heterogeneous material we produce in additive manufacturing, the dog bone style testing is not all the time very accurate because it can gives you good information about the material, but what we need is exactly the localized control. So if we localized certain areas within the sample, will that affect the mechanical properties eventually? And then you can see, for example, for the as-built ones, that we can reach a middle point where it's great, like the plasticity index is good, and then it has a decline. We didn't see exactly the same behavior when we do remelting. So the samples, like average samples, so these are multiple tests, not one, for the same sample, same processing parameters can actually increase. So this also indicates a window where we, if we control the remelting process, we can overcome the decrease in elasticity and then the increase in hardness of the material. And I apologize, I don't know what happened to this figure, but so the other step here is to look at the so the other step here is to look at the specific shape memory alloy specification, like the transformation temperature. And since this is an iron shape memory alloy, you can see that the regular DSC didn't detect great variation in the transformation temperature. And the reason for that is because this system is an iron-based system, and usually when we have iron, we have to do a magnetization test because the increase in temperature will increase the magnetization effect on the material and eventually affect the DSC values. And you can see that we get a good magnetization results for this alloy system specifically. It's not great, but it's an acceptable one comparing to the traditional manufactured one. And that gives us an idea is like what's happening, why we're not actually achieving the same transformation temperature profile if we're doing the same composition. And then the next idea in this analysis is when we understand additive manufacturing is because of material evaporation. So if we looked at the composition analysis of the material, specifically for the low melting point of manganese in this alloy system, you can see that when we increase the laser power, tentatively we will have a reduction in manganese. So there's many manganese percentage that actually evaporates during the print. So although we actually get the same, we put the same alloy composition that's as the traditional one, we have a 3% reduction in the manganese if we increase the temperature or the laser power. And that's not a unique for the system. It's actually a problem in laser powder bed fusion or laser-based additive manufacturing. And there are certain techniques we will want to explore of compensating for the loss of manganese. So eventually the green spots you can see here and then the blue ones will not be very far apart. So eventually reducing the manganese reduction and not losing a lot of the material shape memory effect because of the loss of manganese. And then the next step is to leave you with this idea. So when we control the material, basically, and then control the material properties, localize it, and then basically control it very carefully with the laser powder bed machine or any additive manufacturing machine. The next step is to explore how this will be integrated into structure. So eventually this component or this material will make a final part that will have certain function. So next step of exploration for iron shape or even any shape memory alloy is how to put that with a controlled structure. So understanding the 4D of the design. So what will be the design of the material when it folds, unfolds, bend, unbend, or basically twist or do any certain of functions that's intended to, and how we can control that during the process. So instead of training the material and then do all these steps in order to for the shape memory to remember its original shape, can we do that during the process itself or start this process during the laser powder bed fusion process and then eventually set the part for success and easier and less time. And another steps in this also is the additive manufacturing enable creating creative structures that we weren't able to produce. And one of them is, like, for example, the sandwich structure you see. So what happens if we merge this alloy system with other materials, known materials, through laser powder bed fusion in order to get a unique structure that will behave with a certain needed way. So for example, if we have skin core, or we have a sandwich structure where the middle needs to behave a certain way, and then the outer skin needs to behave in a certain surface conditions, specifically for oxidation resistance. If you need to protect this material at the same time, let it behave for the shape memory superelasticity or shape memory effect, then we can leverage these properties. And these layers can be controlled. So they can be between one layer of like 20 micrometers, or like even larger because of the laser powder capability. So basically the control in the thickness also is not an issue in laser powder bed fusion. So eventually opening doors that we can leverage, like different structures that we're not able to produce, not just because of the complexity, is because of the microstructure scale that we can produce now. With that, thank you so much for making time for me. I'll be happy to take any questions if you have any.
Thank you very much. Dr. Elahinia, are you there? There are some questions in chat. Maybe we can go through them. Thank you very much, Ado, for your presentation. There are some questions in chat. First one from Shiva asks you, have you tried any machine learning technique or any form of process simulation on thermal history result to see if it is possible to predict cooling rate for different process parameters?
Yes. So we did some machine learning with thermal imaging and simulation, but it's not specifically for the iron shape memory alloy. But in this world, there is an understanding or a question that researchers try to answer: is thermal cooling only like a signature for the material, or is it a well-known parameter that across different alloy system we can predict that? That's what the machine learning is actually trying to achieve.
Okay, very well. Second question from Angelo is asking you actually two questions from slide 3 for this FeSMA alloy. I'm curious to know if there is a monotony stress strain curve that shows the maximum strain and stress value at failure for this alloy for comparison purpose with the strain recovery. Maybe you can answer this question and then I ask the second question.
Yeah. So we're still working on that. So this is actually a very fresh results we got. Now there's a new technique we're gonna apply for these specific samples, where we have a micro indentation that correlates to the stress strain diagram. So it's actually measures the microstructure and not only a dog bone style tensile test machine or tensile test sample. So hopefully follow up for more results on the stress strain for these specific samples.
All right, very good. And the second part of question about the slide number 5, I could see that larger grain component had less hardness with more ductility, and the smaller grain had more hardness with less ductility. Do you have any comment on that? Slide number 5.
So slide number 5, this is where the cooling rate effect, right? This is basically a traditionally manufactured polycrystalline shape memory alloy, right? And then you can see that the effect of the different thermal signature of the process yields different grain structure. And I cannot speak of why the grains on the traditional one is actually showing less ductility or higher, but this is a little bit different than the alloy system we specifically used, but it's within the same family.
All right, thank you. Sorry, Dr. Elahinia, I took your role for a couple of minutes. Please go ahead.
Oh, thank you. No, I had some technical difficulty. My apologies. Please keep going.
No problem. I think we have one more question here. I can read for you in slide 14 or 15. Why does the stress decrease in some part of as-built sample and then increase after remelting?
So this is a good question. So you can see when we look at the as-built one, so the purple, like the dark purple one, is that it's not like a line. So sometimes you have an increase in laser power, and then significantly after that, the material behaves actually better, right? So it's not in laser powder bed fusion, it's not like a line. So whenever you increase the laser power, then the material properties increase or decrease. Usually what we find is that because of the thermal dynamics of the melting pool, that will affect what happens after for the mechanical properties. So the remelting is a slower pace with a slower power laser that passes through the layer and then basically improve the mechanical properties. Now, why this happens is in each different laser power and laser speed is because of the differences in the thermal signature on the melting pool. So that needs more understanding on the thermal pool itself, melting pool analysis. So we know, for example, in the lower ones, we may have a lot of certain phenomena happening, that a lot of particles that excites outside of the melting pool or they don't fuse well. That's a certain of information we need from the melting pool analysis.
If I may interject, because we want to stay within the hour, I know there is a lot more questions and conversations, but this is the whole point of opening the dialogue. Please find Dr. Qattawi's contact information on the University of Toledo website. If you have other questions, and please do connect with her. Thank you, Dr. Qattawi. And we go next to Dr. Benafan from NASA Glen. Whenever you're ready, please go ahead and share your screen.
All right. Let's try that. Please confirm that you see my full screen.
Yes,
Excellent.
we do.
All right. Well, hello, everyone, and thank you for the invitation to be part of this webinar. So my presentation here is going to be less on technical data, more on introducing the concept that I'm about to talk about. So I call this the microstructural stability of shape memory alloys by additive manufacturing dispersion strengthening. So just a recap, I assume everyone already aware about shape memory alloys, but I'll just recap quickly the type of challenges that we see typically in shape memory alloys. Here, one of them is the dimensional instability. So for example, when you take an example cartoon of strain as a function of temperature and you heat and cool under some stress, there is this residual strain that develops because the alloy is not stable dimensionally. This is something that you will do for an actuation response, for instance. There is another type of instability, which is thermal instability. So this is something that you get from a DSC, differential scanning colorimetry, for instance. And this cartoon here shows that when you cycle from 1 to cycle n, this thermal peaks not only shift one way or the other, but also can shift on the enthalpy side of things. So these are the two things that most SMAs encounter before doing some sort of strengthening. So how do you strengthen shape memory alloys against two of these? And this has implications to fatigue, durability, and all sort of things. So let's take a look at some solutions here. And I just bin them into intrinsic and extrinsic. For example, the first solution is through the alloy in itself. When we alloy, the first thing you start with is the alloy composition, chemistry. So you add elements, to, let's say, nickel titanium. You make an alloy nickel rich, for instance, so you can do solid solution strengthening, or you add other stabilizers like cobalt or what have you, depending on what region you're looking at. So that's the first line of defense against those challenges, is your chemistry. And then once you have that chemistry locked in, you can go to the second tier, which is processing. So this processing could be in the way of precipitation strengthening. For instance, if you have a nickel-rich alloy, you can age it to bring up precipitation to strengthen it. Or you can do some other way of promoting stabilization via grain refinements or texture or cold work or heat treatment, etc. All those as a second tier because you already have a locked-in composition. And it's a fairly common way of stabilizing the mechanical and thermal response in shape memory alloys. The third bullet there is stabilization via thermomechanical conditioning. So this is could be at the material level, but also could be at the component level, something that we call training. Sometimes you'll hear the word training used out there, or thermomechanical conditioning, or reconfiguration, or stabilization. There's a ton of different ways to point at the same thing. But here it could be using something like ASTM E3097, which is a uniaxial constant force thermocycling. You can use ASTM E3098, which is a uniaxial thermal free recovery. All those techniques can impart some sort of stability from a thermomechanical perspective. So that's the order of it. But some of these solutions not always work. And here are some challenges that come with those solutions. For instance, if you go to tier 1 and we do solid solutions, sometimes by adding nickel to the composition to make it stabler, you lower the transformation temperature. So you take a knockdown on transformation temperatures reaches. As we know, the more nickel you add, the lower the transformation it gets. On the processing side, tier 2, you can do features like precipitation strengthening. But in the case if you have a titanium-rich alloy, nickel titanium, for example, or nickel tihafnium or anything, if it's a titanium-rich side, you cannot effectively precipitate strengthen. You can precipitate the bad phases that will hurt the device or the alloy, but they're not very effective for precipitation strengthening. Precipitates also change the matrix composition. So when you pull the matrix out and the precipitates happen to be nickel-rich, you remove nickel from the matrix, effectively making the matrix a different composition, and therefore your temperatures can change. And the third one in there are some alloys that precipitation doesn't even apply. The case of ruthenium niobium alloys, or some other very high hafnium alloys, for instance, the solution temperatures of precipitates are below the activation temperature. So there is no way you can precipitate anything in this alloy because the activation temperatures of interest are way high, 700, 800, 900 degrees C, for instance. And the training applies to either way. So here we introduce the notion of additive manufacturing dispersion strengthening. And the idea here, and just in this cartoon shows that when you have nickel-rich alloys, for the case of nickel titanium, just as an example, you can do precipitation strengthening, and you can do dispersion strengthening. Okay, and this is what it looks like. The blue line basically identifies stability, and as you go into the titanium-rich region, stability is lowered because you don't have a strengthening mechanism. And when you go to the titanium rich, you can see here, follow the red line, that the temperatures increase. Sometimes we're interested in high temperature activations, but we have to compromise and go slightly nickel rich, lower it because of stability. Well, what if we can keep the transformation temperatures high and increase the stability via dispersion strengthening? So this is the whole idea, is to keep the chemistry intact, like this cartoon shows here. A slight comparison in a cartoon way versus precipitation versus dispersion. In the case of precipitation strengthening, you start with a base material with no precipitate. You heat treat it by aging heat treatments, and you promote precipitation. So what's the end result? As you precipitate, your transformation temperature shift and your enthalpies and other properties change. So now if you look at the case of dispersion strengthening, you have a base material and then you add some dispersoids, it becomes this sort of composite, dispersoid here. In this context, we're talking via additive manufacturing. And then you can maintain your transformation temperatures and you can maintain your enthalpy without heating it too much. And the goal is to, while maintaining temperatures, while maintaining heat flows, you can also get your strengthening effectively. This idea here, how do we produce the manufacturing process of this additive manufacturing dispersion strengthening, came from a couple of colleagues here at NASA GRC. They introduced this concept in the nickel-based superalloys called GRX810, and it's listed here in this nice paper in Nature. So they have used this method to strengthen nickel-based alloys, and they have seen tremendous improvements in these alloys in terms of creep properties, oxidations, and other things. It works tremendously. In fact, that it's becoming one of the going after alloy out there in the industry for this types of applications. So this served to me, to this group here, as an inspiration to go after and try this concept in shape memory alloys. Now the mechanisms are different. In shape memory alloys, we have martensitic transformations. In the structural alloys, you don't have that, and you are accounting on the types of dislocation interactions. That's how you get your strengthening. So in our case here, we have strengthening, but we have also martensitic transformation. So you have compatibility between the austenite and martensites that you have to worry about. You have things about like nucleations of martensite and growth of martensites once it's nucleated. So those things, in addition to dislocation interactions, comes into play when doing such method for shape memory alloys. So let's recap with that inspiration in mind. This is what we are doing with it. So we take an SMA powder, just like this cartoon shows. It could be nitai, or what Professor Qattawi showed could be iron also. And we mix it with some dispersoid. This dispersoid could be yttria, hafnia, boron nitride, or some other formulation that you would like to mix in the nanometer region. This is not in the micro scale or the micron level, but it's in the nano level. Then we take this powder plus the dispersoid powder and we mix it. We mix it using acoustic mixing, or we could use some sort of ball milling also. And the idea is to coat the SMA. In this cartoon, you can see one SMA particle of powder sphere. And then you can coat it with this little dispersoid powders, yttria for instance. How does it work when you do this process from a powder level before we even go to the additive manufacturing side of things? It looks like this. So from the left here, this is the regular powder, just SMAs. There's nothing applied to it just yet. Then we add some weight percent of yttria as shown in the middle here. This is the powder. That the idea here is that the powder is still spherical, but here it has these things adhered to it. And if I zoom in, you can see some of the aspect of yttria coating the SMA powder. In this case, is nickel titanium alloy. And the same concept is used for hafnia or other things. But you can see here, number one, can you coat the powder? Can the dispersoid adhere to the SMA powder before you start any additive manufacturing as a check? And from this data, it looks like we are achieving that process, as was achieved in other alloys like I showed you on the nickel-based superalloys. If we dive just a little more in there with a couple more SEM images, this is particles doped with yttria. In this particular angle, you can see how the yttria is decorating the SMA particle. SMA particle is in the middle, and you can see yttria is decorating, is going around it here, and we're missing the image on this part. But the idea is by applying that particular mixing procedure, which has its own science and how to mix, what time to use, and temperatures, frequencies, and a whole thing that the group here at NASA GRC have defined for the structural alloys, and we're using that applied to functional alloys here to be able to coat the powder in this fashion. So not just the precursor, we have the powder and we have it pre-coated with dispersoids, and then we go to the additive manufacturing. I don't have to introduce the additive manufacturing to this group, but in this particular one, we use the laser powder bed fusion. and you're familiar how that goes. So we just apply the powder that is pre-coated in this case, and we apply our laser parameters, feed rate, hatch spacing, scanning speed, etc., environments, and all those good stuff that we all use in the laser powder bed fusion. But it's not limited to that. You can use E-beam or other types of additive manufacturing as well. Here are some examples of what we are able to build. So first, in the left image here, we typically build samples for little compression samples, and these are known as the GAU blocks, just blocks that have different features like undercuts and sharp corners, just to see if we can build it. This is just a trial. And once where we find the parameters from this small build here with these features and so on, then we go into building components, just like this one is showing. We build in here tensile bars that we go and test in tension, gets machined into dug bones. And we can do a bunch of different compression samples as a function of volumetric energy to vary the rate and so on. So this we're using with 0.3 and 1 yttria. When we look, the goal is, do we vary transformation temperatures doing that? And this is the result. These are alloys with hafnia and yttria, and those colors that match. And what you see here is that with respect to the base alloy, and here I switched just to give you another example. It's not nickel titanium, it's nickel titanium hafnium. So you can apply it to nitide hafnium, maybe iron alloys as well. And you can see that transformation temperatures are within the noise here of the bulk alloys. We don't change it that much. So this is not precipitation strengthening, which you would expect to change the alloys chemistry and therefore temperatures. So here you can keep the transformation temperatures as is as you develop the next phases. So that's the check number one. Transformation temperatures are achieved and we're not affecting them that much. They are within target. The other important piece of information here is, can we get dense parts by coating these powders? You're thinking have density issues and so on. And as with most additive manufacturing, depending on the volumetric energies, you can achieve good or bad densities. And you can see here, the ones on the top here, we're achieving pretty good density actually compared to the binary nickel titanium rod alloy, dense part, not even additively manufactured. That's our reference frame here. And the goal here as result number 2 is we're able to achieve on nearly full dense part with yttria in the materials for strengthening purposes. So that's an density part, and we wanted to look at mechanical data. So mechanical data is shown here, as you can see on the plot on the left-hand side. So number one observation is that the V series simply means a different dispersoid volume fraction. And we wanted to know, if we put X amount of dispersoids, do we affect the transformation temperatures or the mechanical properties? What this plot is telling us, if I look just a black curve here, the heating and the cooling, actually there are two data points, two plots on the same here because they overlap. What we show here that the mechanical data, number one, is nice and not ideally stable just yet fully, but looking very promising as far as stability. But number two, 0.3 yttria and 1 yttria on this alloy here, you can see them right on top of each other. The blue thing, there's also two curves in here. At higher energy density, you can see them start to separate a little bit. So that's the effect of laser and evaporation of some nickels and so on. And this is on the right-hand side, you can see the austenite finish temperature as a function of applied stress in terms of the mechanical properties. And you can see how these groupings are staying together here. And this, when you change the volumetric energy, of course, things change in the microstructure. You can see this grouping stay together as a function of 0.3 and 1, in this case, yttria. And the same observations are for hafnia. So those are some initial results. Like I mentioned, we had, this is fresh from the lab type results. So we'll start looking into it and studying it and understanding what's going on in the microstructures. Hopefully soon we'll have more results. But I'll leave you with some ongoing work that we're trying. Of course, we've done tensile samples, compression samples that look great, but doesn't mean tensile properties will be there. So we want to look into that. Also, we want to map out the effective of this, how effective is this method when it comes to martensitic transformation? given the driver here is not the dislocation motion and so on. It's the compatibility, the oscillate Martensite switching back and forth. Also, we want to understand from a theoretical perspective the coherent, which is precipitates, or semi-coherent versus incoherent mixtures, which is precipitation versus dispersion. Can you do dispersoid and then supplement it with precipitation, for instance, one on top of the other? How does it work? So that's going on. And also, of course, optimizing the printing parameters never ends. So we've been in this business for so long, but that thing keeps going forever. So we're still trying to make it work. So with that, here's our team that's working on this one and a number of people that helped us get to this point in the lab here, along with our interns. If there are students out there, we welcome them to come work with us here and there. And thank you for your attention. I'll be happy to answer some questions.
Many thanks, Dr. Benafan.
Thank you, Dr. Benafan. There are some questions in the chat. I can read it for you. Anwar asks you, is there any way to confirm, as shown in slide 10, that the coating you apply for SMA is consistent throughout all of the alloy elements in the SMA?
Yeah, so it's not segregated. Let me see if I can, slide 10 you said? Yeah, so there isn't necessarily a segregation if you use the right mixing protocol. So majority of the particles are coated in a similar way, and we have bigger maps of this one blown up throughout, and you can see that most powders is coated the same way. So we can achieve uniform coating.
Okay, very good. I hope you got your answer, Anwar. Is there any other question? If you have, feel free to write it in the chat. Oh, we have one. It's quite long. From Angelo. Thank you for the excellent presentation. From slide number 6, the result obtained from dispersion strengthening seems to be promising for future. And he said, yeah, I'm trying to find his question because there's a statement at the beginning. When do you feel that dispersion strengthening technique for NITI will reach its most optimum ability? And do you feel that can be applied also for iron-based shape memory material in future?
Yeah, so I would your first question about reaching a maturity. I think it is reaching a maturity right now in the structural alloys. And we are behind that in terms of the next to it. But there are other issues that us in the industry of shape memory alloy additive manufacturing, we still have some things to fix in terms of additive manufacturing itself. So those things are coming together nicely, and then groups like Toledo group and other groups in the world, your group, are looking into how do we make the additive manufacturing better. And I will wait for that part to come, and then we can add the ODS to its dispersion strengthen, and we can marry the two and mature the technology. Your second question there, I don't see why not. It couldn't apply to iron-based SMAs. Mechanisms are different. Grain structures are different. So there are some things that need to be refined in terms of the alloy itself. But this dispersion strengthening could be applied as long as the adherence happens, as far as the particles are coated properly being an iron alloy.
Okay, very good. There is one more question. Someone asked you, have you considered using other coating methods such as ALD or PVD?
No. The short answer is no. And the reason is this method, a lot was invested in it and it works great. And we have PVD and CVD here at NASA Glenn. We've been talking about trying it that way, but that process changes things on the substrate and could mean some other things. So the short answer is no, we haven't tried it yet.
Okay, thank you. I think we can stick to the time. And
Thank you.
like how what Professor Elahinia mentioned earlier, if you have more questions, you can reach out Dr. Benafan through his email address.
Maybe
Yeah.
one more question. I see a question about, have you conducted any impurity level with relationship to the actual base alloy?
Yeah, a very, very tricky question because we are loading it with impurities intentionally. So we put in yttria and hafnia and boron nitride intentionally. So when we do chemistry, ICP or other methods, for sure we detect those. If you're referring to other impurities other than those, no, we typically don't. The process is done in a clean way that we don't introduce any other foreign elements. But impurities of the dispersoid are for sure there by design.
Of course, yeah. And the second question is there any effect on the grain size? I think the cartoons show probably not, but I defer to you.
We don't have data to answer that at this moment. So the cartoon was mostly, just to convey the idea. But this is something that we'd be looking at how the interaction with grains and grade breakdown, if it occurs, we shall see.
Sure. Did I see Dr. Qattawi's hand go up? Did you have a question?
Oh no, I don't know where I am. Okay, no, I'm sorry. I wanted to clap, but I saw a hand. So
that was a clap.
Yeah.
Well, thank you very much for the two great presenters and for Dr. Mehbooya to start this whole process of this series of webinars. We really appreciate this thought, and we look forward to participating in the future. Please do connect with AM Smart if you haven't already connected on LinkedIn, or subscribe to their newsletter and follow the website. Any closing thoughts, Dr. Mehbooya, before I say my goodbye? It's yours to finish it off. Go ahead, please.
Yeah, thank you. Thank you all for your presentation. Also, Dr. Elahinia for mentoring this session. I would like to invite you to follow the LinkedIn page. We are going to have this kind of webinar every 2 months. The next one is already arranged. I'm going to announce that after a couple of days, and it's going to shift the topic from shape memory alloys to shape memory polymers, but it's still smart materials and same environment. And yeah, I hope I see you also, the audience, in future webinars. Thank you all for your attendance and participant, and also presenter. Thank you.
Okay, thank you, everyone. Take care.
Have a good day. Bye.
Bye.